Today we will continue with the topic of efficient similarity search. We started last time by definition of metric indexing, and today we will continue to approximate searching. First, I will motivate why we should search approximately and not exactly, and then I present a couple of examples, one of category of mapping techniques and the other that is bound to a particular structure that will be M-tree and algorithm for k-nearest neighbor search. At the end, I will also mention pivot tables and something that is specifically designed for approximate search, and that's permutation indexes. So let's start with motivation. As we already discussed, the concept of similarity search itself is basically not exact in the sense that we can precisely define what we want to obtain from a database or from a collection, and because we don't have any attributes that could be matched by some query predicate, as we have this possibility in SQL, for example. So instead we resort to the similarity concept. We have something that is not precise, it's just similar, so we search for similar things. So in this sense, exact searching, that means I will obtain exactly what's belonging to the ball of the query, is something that is more or less illusion, because the problem itself is not exact. So if we lose some of this exactness, we will retrieve something that is a bit of outside of the query ball, or we miss something that is actually inside the query ball, but we don't return this. We will not worse the concept of the similarity search, or we don't change the concept because it's inherently imprecise. But why we should do that? Well, in many cases, the exact search is simply too slow, because the metric indexes, of course, are designed, or other indexes are designed to speed up search, but in some cases it's hugely based on the model of the similarity and on the data distribution. It turns out that it is not enough. So we can maybe save 10% of time when compared to sequential scan, and this is simply not enough. So in this situation, we would like to speed the search much more, but that would be at the cost of exactness of the search. So we will switch to approximate search, and this switching to approximate search is usually under the expectation that we get huge speed up for just a small loss in the precision. This kind of trade-off is for most of applications appropriate, and we get more than what we lost. So this is of course the case that it's worth to switch to approximate search. It's not worth to switch to approximate search if we really lose much of the precision and only get small speed up. Then it doesn't matter, and it's maybe better to switch back to the naive solution of sequential scan, and we get rid of any overhead of indexing and everything. So this is basically the main idea. We would like to massively improve the speed, the efficiency, for just a reasonable loss in the precision. Okay, and what is too slow? Let's specifically talk about what we already have. So we have the metric postulates for the metric indexing, and these postulates are a tool how to construct the lower bounds. We already talked about lower bounds, and these lower bounds allow us to filter non-relevant objects from the search. But these postulates alone do not guarantee any efficiency. This is true for linear indexes, like linear key indexes like B-tree, because there is guaranteed logarithmic complexity, but this is not true for any other multidimensional or metric indexes, because there is nothing like ordering of data, and it cannot be ensured, it cannot be guaranteed for any distribution. So the distribution is really very important. We can have easy distribution. We can have distribution of data that inherently form clusters, and it's nicely distributed, nicely separated, and could be indexed into a hierarchy of regions, and these could be nicely filtered out from search when querying. But we have also databases where everything is basically appearing as noise, so there are no separated clusters of data, and this is very hard to index. And to be able to distinguish between different types of data distributions, we will talk about this as about the ability of structuring the database, and we'll call it indexability. So indexability would be some measure to decide whether, or helping us to decide whether a database is actually indexable for fast search or not. And there are many concepts for measuring this indexability, and one of the most prominent or most used indicator in the area of metric indexing is the so-called intrinsic dimensionality, which itself is an overloaded term. This is really a simple interpretation of intrinsic dimensionality. Basically measure some, as it says, dimensionality in data, regardless real structure of the data. So we could have vectors or strings or time series or whatever kind of descriptors that are not vectors, have no dimension, but we still can measure something that is called intrinsic dimensionality. It's general measure. Now what it is. So as I said, it's a really simple statistical concept, and it works with distance distribution. So we switch from data distribution because we don't know the descriptors, the structure of the descriptors. We are still in the metric space settings, so we cannot see inside the descriptors. These are black boxes. The metric function itself is also a black box function, and what we have is just measuring distances. So what we have to inspect is some distribution of distances within all of the objects in the database or in some sample. And what we can observe is properties of the distribution of the distance between elements in the database. This is generally represented, it could be represented by probability density function of distances within the database, but for computation reasons it's better to realize it using histograms of frequencies for bins of distances. So we have two examples here. If we take a database and randomly sample pairs of data objects, compute distances between these pairs of objects, and then create a histogram for a given quantization of distances, then we can construct a histogram like this. So for example, in this one we see that distance that is the half of the maximum is d plus, so half of the maximum is present in the data set in something like less than 2%, and we have these percentages for all of these distance ranges, and we can then see the overall distribution of distances within a data set. And these distributions vary from data set to data set, and also it's dependent on the metric model, on the metric function. So we can observe different kinds of these distributions, like this one, where there is a white hat. The distribution is it's like hat. It's always a hat, but this one is white, and it's more shifted to the left. And this one is quite narrow, and it's more shifted to the right. What does it mean? In this data set, we can observe many of small distances. These distances are quite present there. And we have also large distances that are also present there, and then we have many median distances. And we could interpret this histogram or this distribution of distances that they are probably clusters, so that's why we have small distances between the objects within the clusters. And we have also large distances that are probably intra-cluster distances, so these are distances between objects from different clusters and something in between. And this suggests that there is some structure composed of clusters, and if we have clusters, it's good because it's indexable. We have separable data set or separated clusters of data, and if you have separated clusters, it's a win situation for us because when data are separated into clusters, they are well indexable. On the other hand, if we have this narrow right-shifted bell or hat, we observe that most or all of the distances are basically larger than the half of the maximum distance. Everything is to the right from the half of the maximum distance, and this is basically a sign of badly or poorly distributed data, because everything is too far from everything else. So they're probably not very good clusters, and mainly we can take it really analytically, and there are all of the distances that are appearing between different objects in the data set are larger than half of the maximum distance. This basically means that the triangle inequality in the indexes that is used to filter out data from search will be completely not effective, because when we are filtering data, we are using the query ball and either pivots for filtering or ball regions, and in all cases we are computing inequality that if, for example, if we have two balls, one is query ball, one is data ball, and if the distance between the centers of the balls is larger than the sum of the both radii of the two balls, then the data ball could be filtered out from search. But from this distribution, we can see that there is no situation like this, because every distance, and this covers also the radii, or both of the radiuses, are larger than the half of the maximum distance, also the distance between the centroids of the balls. So we cannot achieve a value that will not basically break a triangle. So there will always be overlap between the two balls. So this distance distribution is completely non-indexable, or the database data sets with this distribution is non-indexable exactly. I talk about exact indexing now, and we can quantify these distributions into the intrinsic dimensionality by, as I said, statistical measures. So it will be just simple ratio of square of the mean of the distributions, which is, for example, here in this case, and the variance of the distribution, which is large here and it is low here, and here is large the mean. So the smaller the mean and larger the variance, we get smaller intrinsic dimensionality, which is here. We have low intrinsic dimensionality because of this distribution. And on the other hand, if there is a large mean of distances like here and a very small variance, we get large or high intrinsic dimensionality. And this, we get a single number, and we can just use this number for decisions or comparisons mainly between different distributions of data. Of course, this number is not bounded from the right side of the interval. There is no bound, and there is also no. It's basically measureless number. It doesn't mean that it's really dimensionality like in the Euclidean sense, but for Euclidean data, uniformly distributed Euclidean data, it roughly matches. So if we have, for example, 10-dimensional data set, 10-dimensional Euclidean data set with uniform distribution, this intrinsic dimensionality will be more or less 10. So we have a clue about the some virtual dimensionality if the data is Euclidean data, something like that, but it's not precise. But what it is good for? Well, the main message is if we have intrinsic dimensionality that is very large, and this is something, let's say, above 10, then we have a sign, like in this case, that no exact indexing, regardless of metric index, will work for fast search. Just because what I just said, because of the triangles and the distances that are too large, it will, no matter of design of the metric index, if the hashed index, hierarchical, whatever, the data is just too unclustered. It looks randomly to be separated. So in this case, what we can do, we can just say, okay, we will not build any index on this because it would be just overhead or waste of time. Or, and that's our today's topic, we can resort to approximate search. And in proximate search, we will basically trade in these terms of the intrinsic dimensionality, we will basically trade the distribution for precision. So we will do something like turning this bad distribution into this good, but with losing some information. So we only get approximate results at the end. Okay, but we already said that making approximate search from exact search is not some disaster, because we already start with imperfect models. Similarity is imperfect, it's just similarity. So let's continue with this relaxation to the database part of the search. We will of course talk about exact and approximate search, but this is just a technical term. Exact search means that's a referential search, or a referential search that could be just the sequential search. So sequential search is exact in the sense that the data that are in the result of sequential search all match the similarity predicate. So for example, for range query, everything that is in the result matches the predicate that it's inside the query ball. Nothing that is outside the query ball appears in the result, and nothing that is actually inside the query ball is not returned, cannot happen. So in this sense, the search from the database perspective, from the algorithm, is exact, but it's not exact in the overall terms of precision recall, because this is subjective. Okay, so we can turn from exact search, where the reference is the sequential search, to approximate search. So we allow now to return results that are not exactly matching the results that would be given by sequential search, but because all of the problem is not exact, this maybe should not worsen the applicability of the search as a tool. Of course, it cannot be unbounded, uncontrolled loss of precision. We can talk about different types of approximate search where we control how much the approximation will go basically far from the exact search. And that's what we discuss now. So what is basically approximate? We can define many definitions of what is approximate, and the strongest definition would be that we have a guarantee of a bound for every individual object in the query result. So this is really the strict interpretation of approximate search, where we will demand that every result in a method that is approximate will return objects that all of them are not completely bad. So all of the objects in the result are somehow relevant, are somehow not so imprecise. So this is individual bound. Of course, this is very strict. We do not allow any garbage in the query result, and so this is also the less effective approximate in terms of speeding the search, because we have quite strong bound. It is not so far from exact. This is something, basically this is like a bit relaxed exact search. We only allow a bit of error to every individual result, but that is control. Then, if this is not enough, and it mostly will not be enough, because, as I said, it's not so aggressive to speed up the search much, then we need to resort to less guaranteed searches, and basically the well-known or used concept for this is probabilistic estimate or probabilistic guarantees for approximate search. So we relax from the guarantee of every individual object in the query result. That should be more or less good, but we will only demand that statistically every object in the query result is good. So we have only probability that is guaranteed in long-term run that the queries are correct or relevant to some extent. So we cannot guarantee anymore anything about individual objects in the query if we have one. So classic probabilistic guarantee, and of course we could have also no guarantee, which is weakest. We don't have any model of the error, and we just experimentally observe the results of the methods, and just after a number of experimental observations we can basically formulate some estimates of the error, but we don't have any underlying theory for this. So this is mostly used for cases where we don't know, we don't have any sufficient input for creating, for example, probabilistic theory, because in this case, in the probabilistic estimates, we need to know for example, the distribution of the data, and most of the probabilistic estimates work with normal or uniform distribution, and this is not the case of real world data sets. So even that we have probabilistic estimates, they are mostly not matching the actual distributions of data, so we must take them with reserve. So what we basically mostly use is this no guarantee, just empirical techniques. Okay, and we have the approximate definitions, and now basically how to speed up the search. So speeding up search means, of course, we reduce the real time to finish the query, and in consequence, this also means, in the sense of the previous lecture, that we reduce the numbers of distance computations. And there are many techniques how to do that. And basically, what we do is two things. We first could alter the algorithms that are designed as exact search algorithms, and just alter them to be more aggressive when filtering, with the risk that we during this more aggressive filtering we filter something that should not be filtered, but the algorithm will finish sooner and the real time will be smaller. That's one possibility. And the other possibility is more on the model level. So we instead of resorting to some particular algorithm, we basically transform the problem on the high dimensional problem into some lower dimensional one. And now I talk about intrinsic dimensionality. So And then I can reuse any other indexing techniques and other algorithms. So this is more general approach. So transformation of the input hard metric space into some simpler but only approximate space. So we don't have one-to-one transformation, but we lose something. So we get approximate search. In traditional spatial databases, this is realized using so-called dimensionality reductions algorithms. So we take high dimensional, in Euclidean sense, high dimensional space and turn it to lower dimensional space, just turning, I don't know, 1 million dimensions into 100. But in metric space case, which is our case, we do the same, but not as using the techniques of dimensionality reduction, because we don't have vectors. We have objects of metric space, so we need to do it appropriately for metric space. Okay, so but these are two categories. We start with categories. The second category is category which is mapping techniques. So making a space, turning one hard space into some other easier space. So we can do this by different methods. We could really map the whole space into completely different space, such as we basically map metric space into vector space, and of course under different distance functions, because in metric space we have, for example, strings and edit distance. This is the expensive space, for example, and we turn it into Euclidean space. So in Euclidean space we have vectors, not strings, and we have, for example, Euclidean distance and not edit distance. So this is complete turnover of the space, or mapping of everything. We could also only map the space in the distance domain. We could only change the function delta and keep the descriptors. So we can take hard metric space and turn it into easier metric space, for example, by replacing the delta function with its cheaper lower bound function. And this is also how we get faster search for some approximation, and the approximation is hidden in not using the original distance but just lower bound. We already saw that lower bound distances for indexing are only approximate, and that's why we would get also approximate search. But either way, we need to do some pre-processing of the database, and we can distinguish between static or dynamic mapping. In the static, we need some more information, like we have data dependent. So we first analyze the data and then create data dependent embedding scheme. Embedding means basically mapping from metric space into some Euclidean space, is embedding. Or we don't analyze the data, but design a mapping scheme that is independent on the data. And for example, we could see pivot tables as this data independent mapping scheme, and we will talk about this later. We already talked about this in the previous lecture, because it was a standard exact search method for metric spaces, but we can use it also for approximate search. And the nice about this mapping approach is that the target data, the data in the target space, could be individually or independently indexed by whatever indexing scheme that is suitable. So we can use metric access method or spatial indexes on the new kind of data. So we will basically decompose the problem into two steps: mapping to some easier case and then indexing this easier case. For this, in this sense, there will develop many mapping techniques. They mostly map the data, the metric space data, into Euclidean space. And the best one is very old, 70, 80 years old, and it's called metric multidimensional scaling. That is basically optimal with respect to preserving the overall distance distribution of the original data. So with metric multidimensional scaling, we get, given a user-defined dimensionality, we get the best result in terms of cumulated overall error of the distance. I now talk about error in the preserving the distance distribution. So if we measure distances in the original space and in the target space, metric dimensional scaling makes this transformation that produces the lowest error in the target space. Of course, it's not zero, because if we reduce from 1 million dimensions to 100, we get error, but this error is the smallest with metric multidimensional scaling. But the algorithm is actually very slow. So there were developed many methods that approximate the metric multidimensional scaling for a much shorter time, and one of them is FastMap. Others are metric map, sparse map. There are many something map approaches that map basically metric data to Euclidean data. I will talk about FastMap, which was the first one, and it's called fast because it's faster than the metric multidimensional scaling. But actually, when compared to the newer ones that are metric map, sparse map, it's basically very slow. But it already had reserved the name FastMap, so it's called FastMap. And it's also quite nice example how basically high school mathematics could be used for mapping metric spaces into Euclidean space. But first, I will just present the very straightforward example how we can do very easily approximate search using a technique that is designed for exact search, and that is the LISA algorithm or pivot tables. We already saw this picture. We had we start with the data in metric space and then select some pivots, in this case 2 pivots, P1, P2, and transform the data from the metric space to pivot space and get this distribution. And it's contractive mapping, as we already discussed. That means distances in the target space are lower or equal than distances in the source space, so they more or less approximate the distances here. So for us, it is approximate embedding, and the source distance was some function delta, and the target distance is L max. So we have vectors and L max, and here we had completely generic metric space. And what we get, we already discussed the LISA or the pivot tables algorithm that could be done. The k nearest neighbor. We have now example with the 2 nearest neighbor query, and the 2 nearest neighbors basically are, which is not the case of here, because here we have range query, but here we have the same situation that we have in the example that we used last time, but let's now have new query that is 2 nearest neighbor query, and that would be in this case O1, 2 nearest neighbors. So it's O1 and O7 apparently. The 2 nearest to Q is O1 and O7, but because of this mapping that is not exact but approximate, we get in the new space 2 nearest neighbors, not O1, O7, but O1 and O4, because of this mapping of O4 using these 2 pivots very close to O1, because based on the mapping scheme for the pivots, these 2 objects are almost interchangeable. They are all the same distance from P2 and from P1. So that's why they are close together in the target space. And this is the approximation. We could also, if we omit the second filter phase, which would follow the mapping phase for exact search using pivot tables, then we need to check all of these candidates to nearest neighbors in the original space, but we only get O1 because we have only 2 candidates. We have just O1 and 04, and in the original space this is just 01. That's the correct answer in in 2 nearest neighbor search. The second would be 07, but we don't see 07. So we can omit the second step and get basically the answer as the immediate answer to 2 nearest neighbors query. So we get 01 and 04 and return this as a result of approximate 2 nearest neighbor search. Why we do that? Because the filtering phase is the most expensive phase that happens in the exact search. And if we only realize the first step, the mapping, we basically get very cheap query, because what we need to do is map this Q, the query object, using the 2 pivots. That's 2 computations of distance, P2Q and P1Q. We have this mapping, and then we have no other distance computations because of the expensive delta. We have only the Lmax computations that are cheap, and we only return what's inside, and we don't need any other computations in the original space. So basically it's very cheap. For just 2 computations we get the result, and this is a huge speed up in the real situation. Of course not in this textbook example, but in real situations. So this is basically how exact search structures and techniques could be adapted for approximate search. It could be very easy. It could be just omitting something, like in this case. In some other cases it would be more complicated. We will see it in M3 later. Okay, so this very simple technique, will it work or not? Of course it will work for to some extent, because the Lmax distance is lower bound to delta in the metric space, so it is some approximation of delta. So in this sense it's approximate search, and it will be as good approximation the more of good pivots we will have, because if we look in the situation, we have just 2 pivots, and because there are just 2, it is not very good approximation. The Lmax is not very good approximation for example, the distance between 01 and 04 that are very close here and very far here. So this is very large, and this is very small. So it's not good approximation. But once we add more pivots, because 2 is apparently not many. For example, pivot P3, that would be somewhere here, for example, then we would get completely different situation, and we will have distance from P3 here to 04 here. It will be just small, and very far here, and therefore in 3-dimensional pivot space, because we would have one more pivot, this 04 object will fall out of the cube, or ball, but it's cube, of the query, and therefore the distance would be much larger than here, and in turn the approximation of these distances by the Lmax using more pivots would be much more precise than using a small number of pivots. So that's how to improve this technique. It's also how to improve the exact search, but it's the same. So we with adding more good pivots, we basically tighten the lower bound, and this means 2 things. We can improve the exact search and also the approximate search, because tighter lower bound means better approximation of the distance. Of course, we cannot do it for some extreme numbers of pivots, because then we get the overhead of mapping much larger than the speed up. So there is some optimal number of pivots and so on, but this is beyond the discussion. Okay, and what is important, we have no guarantee of any precision. We just have empirical indicators for this. We will later present something that is probabilistic bound, but it is not this simple case. Okay, so let's go to the mapping techniques and to the FastMap, as I said. And this is very nice example how we can use two simple laws from high school mathematics, and that's the cosine law and Pythagorean theorem. And using these two, we can basically pretend that the distance distribution of the data or the data is basically in Euclidean space, but we have only distances between them, and we need to reconstruct their coordinates using these two techniques. So basically what we are doing, we are just transforming representation of vectors that we have only in form of distances between them into the actual vectors. Of course, this is just a fake because we have metric space on the input, so we cannot recover vectors for metric objects, but basically this is the trick of the method. So we pretend we have just the distance distribution of some metric space, but we do it for of some vector space, but we do it for metric space. So how it's done? The algorithm works quite easily in 4 steps. In 0 step, we just set the number of dimensions we need to use. So the target dimensionality of the Euclidean space we construct will be k. And then in the loop, the first step in the loop will be selecting the best pivot pair in the data set, and the pair will be constituting something like axis of a coordinate system. So we will create coordinate system for vector space, and we need to do it somehow. So we do it by selecting some object at random, completely random object O, this one. Then we search for the farthest objects from O, that is P1, and then we search for farthest object from P1, that is P2. And these two objects for something like axis, but of course we are still in metric space, so there is nothing like axis, but let's pretend there is axis. It will basically that's the illusion of the method of FastMap. So we have something like axis, some virtual axis, and now in the second step we just project all of the data to the axis and get a coordinate. How we can do that? What we know, we know because we have distance-based representation. We only know distances between individual objects because these are not vectors; these are metric objects. So we don't have any coordinates, right? So what we know is distances between objects. So we know distance P2x, we know P1x, and we know P1, P2. So this triangle. But in FastMap, we basically will reconstruct coordinate of every database objects by projection of the objects on the axis. And how we can do that? Well, that's the role of cosine law, because in cosine law we have this formula, it's well known, and everything we know except this coefficient Cx, that basically could be computed using the distances we know. So using the distances we know, we basically compute this projection of x, this orthogonal projection to the axis, and this number we get is basically a coordinate in a new dimension we obtained right now. And the origin of the dimension is here in P1, and it's just this value, and we get one dimension and or the coordinates for all the objects in the dimension. So this is first trick. And now second trick, because now we need to keep constructing the axis. But if we just return back to step 1 and again select next best pivot pair to next dimension, this dimension would not be orthogonal. It would be, for example, this and this, P1 and P2 here, and it would be like this, and this is not orthogonal to the original axis. So what we first need to do is step 3, and it's update of the function delta to basically make the already processed dimensions out of the system and basically only restrict the orthogonal plane or subspace. So we cannot select in the first step next because it will be next loop. some non-orthogonal axis. So how we'll do that? Basically, we will not do anything with the dimensions we already computed, but we update the original function into a new one, basically by the Pythagorean theorem, and it's shown here. We have the projections to the P1, P2, and then we need to construct other axis that is orthogonal to P1, P2. So we need to only choose from representations of the objects that are in this orthogonal plane here, or plane it's in this case, but it's orthogonal subspace in general. So, and we will do it by Pythagorean theorem. So we will project everything using the distance into the orthogonal plane, and then we'll freely work within this plane using this d prime, not the original delta. And then we go to step 1 and everything repeat again. And we keep doing these steps until we have k dimension, which was the user-defined parameter, and we have all of the axes orthogonal. So we get really orthogonal system and orthogonal projection, and that's why it will work, and that's why it basically approximates the metric multidimensional scaling, because the base is really orthogonal. So this is FastMap. Now I will devote time to the second category, that is basically altering of algorithms that were originally designed for exact KNN search or exact search for approximate search. And let's start with M3, because M3 is a very easy structure and could be used as an illustration how it can be done. So, but first we need to present the exact version of the KNN algorithm, because then we will alter it to the approximate version. So first we need to know the exact version. We didn't describe it in the previous lecture, so we need to do it now. So in exact KNN algorithm, we search exactly for k nearest neighbors, and for this the algorithm basically needs to pretend. Basically, the algorithm is based as a range query, but range query that doesn't know the radius, because we don't know the radius ahead. We just know k. We know k nearest neighbors, but no radius. So the heuristic behind the algorithm is that the radius is infinite, and during processing the query, we reduce the radius from the infinite values is reduced to the actual value of the kth nearest neighbor, and that's the stopping radius. It's the final state of the radius. So for this reason, there is iterative reduction of the radius. We need two structures in the algorithm. That's a priority queue PR. It's priority PR priority queue that maintains basically a queue of requests for processing, and these requests basically are nodes that need to be processed and cannot be excluded from the search. And these nodes, of course, map to the regions. So we have these structures M3, and this is the metric representation or representation of the M3 in the space. And we have here the query queue. We don't have any radius because we don't know radius for k nearest neighbors, so we start with infinite radius, and we basically need to process all of the balls here that cannot be excluded from the search. So in start, nothing can be excluded in the search, and everything should be in the priority queue, which is basically the root. So root will be the first entry there. And second structure that we will keep in the algorithm is so-called NN array, and that's basically array for the candidates to KNN. So this array has a fixed size, it's k, and there only will be updated the best k candidates for the nearest neighbors. And now how the algorithm works. The idea is that we consider the range query, as I said, but we don't know the radius RQ. So we set, we will view this this radius as dynamic. So we have the dynamic radius that will start on maximum, so it will be infinite, and then basically it will be reduced by processing the request from the PRQ. So the PRQ at first just contains the root of the M tree. We have no candidates for nearest neighbor, so we have empty array, and then the M tree is traversed based on popping request from the PRQ. So every request is basically in the form of a node, so it's unwrapped, and the child nodes are again inserted back to the priority queue, and so on. And during this process, they are updated both the dynamic radius, that is radius to the kth nearest neighbor candidate, and also the PRQ, of course. And we have also information to the request in the PRQ that will be the lower bound to the node, to the ball. And if the lower bound will be larger than the dynamic radius, that means it's outside of the query ball and could be filtered out. And this is the basically principle how the algorithm works. Okay, it's better to show it on example. We have the situation with this example. We have a query that is here, and we search for two nearest neighbors. So that's why the NN array has two positions, and we start with the PRQ, where the first and only entry is the root. So it's the whole tree, the root, and now and the radius is set to infinity. So query radius starts somewhere here, so it's infinite, and we start to process. So every step starts with popping the entry in the PRQ, that here is root in the first step. And what I didn't say is that we observe some distances here, and these are no distances, these are bounds. So we have upper bounds of the candidates. So now it's infinity, and this is the distance to the second nearest neighbor, and we don't know anything, so we must assume this is basically infinity, because we will only then reduce this distance in the algorithm. And the second, what we observe here is the lower bound to the ball of the request, and in the root we don't have any ball, so it's also infinity. But so we read the root, we get two entries to two subnodes, 1 and 2, and we have updated everything. So we read the root, it's already off the PRQ, and instead its children were inserted in the PRQ. That means 1 and 2, and these are inserted in the PRQ in order, that's why it's priority queue, by these numbers, which are basically lower bounds from the query to the region that belongs to the nodes, to this node and to this node. It's 1 and 2, and because the lower bound of q to 2 to the second is 0, because it's inside, it's 0, it gets to the first position, and the second position will be the ball 1, that is this far, based on the lower bound. So this is lower bound distance. We keep observing lower bound distances in the PRQ and keep the order based on this distance. So that's why it's priority. It's always be the lowest lower bound in this place. And why is that? It's because the probability that a nearest neighbor will be in the closest region is higher that it would be in the farthest. So for Q, it is more likely at this level of processing we only see these dotted circles, nothing inside. We only see dotted circles. So based on dotted circles, the probability that there will be nearest neighbor in the 2 is higher than it will be in 1, because Q is already in 2. So that's why the processing of 2 will be sooner than the processing of 1. And we also update the candidates to nearest neighbors. We have still no candidates at the leaf level because we are still here. But we can use these positions just to keep the radius. And the radius cannot be larger than the upper bound to the second nearest neighbor. So now we are just working with balls, these dotted ones, and the first is closer, this one, so this is here, and the second is farther, so this is here. So for us this is candidate to second nearest neighbor, but only approximation because it's just the ball, because we start with the upper levels. Okay, so and we have upper bounds and lower bounds, and basically the filtering principle is simple. Once this upper bound is smaller than any of these lower bounds, then this means that the query ball, which is basically, this is also the radius of the this is basically the radius of the query, right? Then when this is smaller than anything here, it could be filtered out from search because it cannot match the query and the query ball that is getting smaller and smaller. Yeah, so now we just process. So next we process 2 because it's on the front of the PRQ. We read children, so D and C. Insert it again back to the Q. What we get? We get new lower bounds. From Q we get for this one for D and this one for C, because this one is smallest, because we already processed 2. Then now this is the smallest, so it's in the first place. This is the largest. It's on the third place because this is the middle one. We still have lower bound to 1, which is this, and this is smaller than this, so it's in the middle. And we also update the nearest neighbor array by the upper bounds. So we have these upper bounds. So one upper bound is to some objects in C, and and the other is some objects in D. So the farthest possible second nearest neighbor is at this distance, so it drops, the radius dropped to here, and we still cannot filter anything because it's still too large to match everything. But we keep processing the Q, so we will fetch another, it's D, and we already have objects on the leaf level, and it's 05 and 06. And this is a huge improvement because once we get at the leaf level, everything will get much tighter. So now we get some real candidates to two nearest neighbors. So we have 05 and 06 as these candidates. So again, we updated everything. So distance from Q to 06 is the new radius, and because of this upper bound is now smaller than the lower bound to A, we can basically filter out A from search, because this dynamic range query cannot anymore overlap the region A. It will only get tighter and tighter. So this is one filtering, first filtering of this algorithm on this data, and we continue more. So what's next is the node 1, but we already filter out A, so we get B, and we update B to PRQ and compute the lower bound distance. So this is this one, so it's first on the in the order. So we get unwrapped B, get another node at the leaf level with objects 03 and 04, update NN, and basically this is the last step because we updated to 04 and 05 as the candidates, which is 04 and 05. Because of this, the radius dropped to this value, and the C region that was still in PRQ was filtered out because the lower bound of C was larger than the upper bound to 05. So we're basically done, and the final answer to exact two nearest neighbors to this query is 04 and 05, and we filtered out just two nodes from the search, but this is very easy example. In reality, the filtered nodes, leaf nodes or other nodes, should be majority, 99% or something like this, of course, if it works. If it doesn't work, then that's the reason for approximate search. In approximate search, we have only a few filtered nodes, and it's not enough for speeding up the search, and that's the reason why we need to switch to approximate search. Okay, so this is the exact version of the algorithm, and now we show how this algorithm could be altered to approximate KNN search. And we can show it or demonstrate it on the same algorithm and use basically 4 different heuristics. First is slowdown of improvements. That means there are iterations in the algorithm. We already saw that there are iterations. They are popping the request from the priority queue and updating the NN array. And if this updating leads to slower and slower improvement of the candidates, because the candidates are somehow far from the query, and if there slows down the improvements of lowering the distance, then maybe it's better to stop and return a candidate that is good enough, because the actual nearest neighbor would be better, of course, but not so much better. So maybe it's good to speed up the search by giving up sooner and return what's already in the NN array. So this is first heuristic. Second heuristic is approximately correct search. That basically is the representative of the strict bound. We talked in the beginning that there will be guaranteed a bound for every result in the k nearest neighbor search to be at most a factor that is factor of the distance to the true nearest neighbor. So it will not be farther than a user-defined factor. So that there will be the strict. This is the strict definition of approximate search. Third heuristic will be about good fraction approximation. It will be about guessing based on the distance distribution where the algorithm can stop, because we probably searched enough of the database to find in average case the nearest neighbor. So if we already search this, we stop, because it's probably not be better if we search more. And then the last one is PAC queries, which is acronym for probably approximately correct queries, and this is basically just combination of approximately correct search and probability methods, and in this case it will be the good fraction approximation, which is a probability method. So we basically chain 2 approximate techniques to even more approximate techniques, but this is most aggressive, leads to most fast search, but also gets most of the imprecision and the errors. So the first one, in the algorithm, we saw that in the algorithm there is a cycle. We are updating the during the algorithm there is updated the NN array, and we are specifically interested in the kth entry in the NN array that basically stores the radius of the dynamic radius of the range query that goes from infinity to the actual distance to the kth nearest neighbor. And we can basically draw this updating value of the radius as a function in time. So in time we have the algorithm iterations, and the and the dynamic radius, which means distance in this kth entry, goes down from infinity. Of course, infinity is not here, but the second basically the first real value is here, and it somehow goes down. Of course, this function is continuous, and it's not continuous in the algorithm, is discrete, but just to imagine the idea, we have a function, and during the algorithm it starts to slow down. The improvement starts to slow down because, for example, here the distance to the real nearest neighbor is here. It's the value where the algorithm gets at the end. But we already see that we already have something that is very close. So this is a candidate of the kth nearest neighbor that is almost as good as the nearest neighbor. It's just this far from it. And we might decide that, okay, it's good enough. Let's return this candidate that is this far from k, then the actual k nearest neighbor, and we spare half of the time. We see that we are half of the runtime of the algorithm here, and we decide, okay, this is enough. We are okay with this approximate candidate. And how to do that? If we model this slowdown as a function, then we can accept some user-defined parameter kappa that will basically be the angle of the tangent in each of the point of the algorithm and the time axis. So as apparently this slows down, so the angle gets smaller and smaller, and once it's smaller than some kappa, that's basically the threshold that's the decision point that basically is used for stopping the algorithm. So this is the slowdown of improvements heuristic, and we can get faster search for some approximate result. Of course, this has no at all guarantee because this is just some artificial criteria. It's just angle. It's not probabilistic bound, no approximate bound, nothing. It's just the relative bound of the angle. Okay, so this is slowdown of improvement. Second heuristic is approximately correct search, and this is the one where we are guaranteeing that at the end, in the result of the query, there will be nothing that is completely useless. So we will keep some level of preciseness for each of the results. And in this case, this will be defined that we have some user-defined threshold epsilon that is a very small number above 0. And the task that we solve now is defined as 1 plus epsilon kn search, and this means that we basically return nearest neighbors that are allowed to be up to 1 plus epsilon times further from the query than the real nearest neighbor. So in other words, we can get to the result something that is to a small factor that is a bit larger than 1, factor that is a bit larger than 1, farther from the actual nearest neighbor, but it's controlled by epsilon. And in the algorithm, this is reflected by the adjustment of the new of computing the new radius. So once there is radius computed from previous state, for example, infinity to some smaller, then we will not reduce it to the exact value, but we will reduce it more. We will reduce it here, and this is the formula. So we will not we will basically reduce it to the right level, but even more to the factor of 1 plus epsilon. So we get here, and at the end we can see this one particular step in the algorithm. What does it mean? We basically see that at the end we get object 04 as the final nearest neighbor to Q, and it's obviously false because the right one was O2, it is closer than Q. But because we have limited this jump that is bounded by 1 plus epsilon factor, we are not jumping to something that is completely out of the bound. So we are guaranteed that the O4 is up to the factor of 1 plus epsilon, not further than a factor of 1 plus epsilon with respect to the O2, which we can see. Everything that is here could be missed, but once there was object here, there will be another reduction of the radius needed, and it will be not O4 but maybe O2, and of course depends. So this is the effect. We get O4 instead of O2, but the O4 is not that bad because it's just limited by the 1 plus epsilon factor. Okay, so this was the second heuristic. The third heuristic is good fraction approximation, and that's heuristic based on the distance distribution, and it basically assumes that we know or we observe the probability of that two distances are below some threshold r. Of course, this is radius, this is query radius, and we compute from the distance distribution on the data this function that says with increasing distance what is the probability, or in this case the frequency of these distances in the distance distribution that are below the r. So r is here, right? So of course, if r is maximum, everything 100% will be below r, and yeah, and if zero, nothing will be below zero, and in between there is some distribution. And we use this function that is pre-computed for the KNN search, and for every update of the query radius, we already know that the radius gets down from infinity to the actual value to the k-nearest neighbor, but every time it changes, we look into this function, and we can look if we already saw the fraction of the database that is typical for that r. So if we have r equal to this value, we know from this function that most of these queries need to search, let's say, half of the database. Then if we already process half of the database, then we stop. So the database fraction that is estimated, and if the estimated database fraction exceeded some user-defined kappa, which is basically what we allow to search. For example, we say we allow for this query to search I don't know, at most 10% of the database. So once it's exceeded, that the 10% of the database was probably inspected using this distribution, not what was already saw, but what is under the distance constraint. So in that case, the algorithm will terminate. So this is good fraction approximation search, and the last one is combination of the two, the 1 plus epsilon nearest neighbors and this good fraction approximation. If they are combined, so there are two effects. The jumping of the radius is faster because of this 1 plus epsilon factor of jumping, and the terminating condition of the KNN algorithm is terminated earlier because of looking into this fraction of the database that was already processed. So combine these two optimizations result to probably approximately correct queries. This is basically funny because it's approximately correct queries, but only probably approximately correct queries. So there's two levels of approximations, but it leads to fastest search, but also largest errors. So these were the methods in KNN algorithm for M3 and the alteration. And now we look briefly to others, and it's approximate search in pivot tables. We already saw in pivot tables the naive technique that we just omit the second step, but we can also design another technique that basically is probabilistic. And this is another view on pivot tables based on just a single pivot. If we have a pivot P and we are now in the metric space view, then what we actually need to process in the database is everything that falls into this ring, because we have a query and we have data, and data are mapped to the pivot. So we have a mapping to a line because we have now number which is distance to the pivot, and everything what is within distance to the pivot in the database from delta PIQ minus R, so from here, to delta PIQ plus R, that's basically in the radius, in the interval that needs to be inspected. And the approximative technique to this is basically thinning this ring to a something that is smaller, so the interval gets smaller. It gets reduced by some beta, and therefore the searching is in small intervals, so there is much more data filtered out from search instantly. So this is this data and this data. So if this is thinner, more of the data will be filtered out, and the search will be faster. And the beta is computed not just ad hoc, but it is a probabilistic method that is guaranteed, and the guarantee is driven by user-defined threshold delta. So we as users define delta parameter. So this means the probability that the search is correct. So we have a correct search with probability of delta. That's what the user says. For example, 0.9, 90% probability that it will be correct. And using this parameter and also other parameters like the number of pivots used, because this is just one, but there are multiple pivots, of course. So this is number of pivots P. There we have the delta, that's the user-defined threshold. Then we also have the sigma, which is variance in the distance distribution. So now it works also with distance distribution. And of course, the radius of the query, RQ. Then we compute the beta, which is basically just a lower bound. And the beta now is working here as the reduction factor if the beta is computed like this, we have statistical probabilistic guarantee that the results will be with this probability correct. So this is another way how to use pivot tables for approximate search. And last, what I want to say is permutation indexes, which is very interesting, completely different approach, and but it comes out from the concept of pivot tables. We already saw pivot tables, which is just a matrix, distance matrix of distances between the objects and pivots, but it takes a lot of space because there are real numbers in the matrix. If we want to speed up the search, what we can do is to compress somehow the table, and instead of real values for each object to all of the pivots, we can just remember in the table the permutations of the pivots from the closest to the farthest. So instead of the real values to the pivots, what we already have in the pivot table, we can just say, okay, I don't care the real value of the distance to the pivot, but I only want to see the ordering of the pivots. And this is basically permutation of pivots with respect to an object. The object is in space and has an order of pivots from the closest to the farthest. And this is permutation of pivots. And this is the line now in the table. So the pivot table turns to a permutation index, which is basically just another table, but with permutations of indexes, not the real values. And in this, using this, we basically can still approximate the metric space, not with real values, but with permutations on pivots, but we really save much of the space, because in pivot tables we need, if we only take 4 bytes per real number, so a float, we have float is 4 byte real, and we have 32 bits times k times n. K means k is the number of here in this sense, this is the number of pivots, and n is the number of objects. So we have 32 times k times n. And in permutation indexes, we basically need less pivots for representation of the permutation. So we get from 32 to logarithm of k. And k is a constant, basically it's the number of pivots. So it will be much lower number than 32, this logarithm. So we get more compact storage. But now what to do with the permutations? We basically can define similarity on the permutations that basically approximate this similarity in the Lmax space in pivot tables, and the Lmax space again is approximation of the original metric distance. So we have this two-step level of approximation. But what does it? What basically we do is measuring for 2 objects U and Q the similarity of their permutations, or of similarity of permutations of pivots with respect to U or Q. And this could be done using Spearman row or Spearman foot rule. They are quite similar, and they have in common this subtraction, where we are basically determining the position of ith pivot within the permutation, and basically and we are doing this for the permutation for the object U and for the query or for other object. And if the position of the same pivot is completely different in one permutation and the other permutation, then probably this is a sign that these 2 objects are far from each other, because they see the pivot in different order than other pivots. So they are probably completely far from each other, that then they see the pivot universe from completely different sides. So there is different ordering of pivots. And this is something that approximates basically the metric space. So the more pivots we have, the more the larger the permutation is, and we sum up at the end the number of the differences between the positions of the same pivot, and sum up it into a distance. So again, we have a distance that somehow approximates the former or the original metric distance. But we switched from geometric framework to combinatorial framework. But the combinatorial framework, as we see, basically mimics or follows the distribution of the metric space, because it only turned into from real values measuring of distances into measuring the differences in positions in permutations. But basically there should be a high correlation with this. Okay, and for the end, I have also some experiments to see how it's effective. Just now summarize. It's basically what I said. This is one more step beyond the pivot tables. Instead of Lmax on vectors, I have Spearman row or foot rule on pivot permutation. So we get to even more to compressed version of pivot tables, basically. And this is essentially from the beginning approximative index. I cannot make basically exact queries with this index, because we lose the real values, but because of the permutations, it will be correlating with the metric space. And now the results, I said, let's have some data sets, different dimensional. So we have data sets from 128 dimensions to 1000 dimensions. It's real dimensions of some vector data set, and we have 2 numbers of pivots. We have 128 pivots and 256 pivots, and we see all of the combinations of metric indexes on these different dimensional data. And we can see that, for example, on 128 dimensional data with 128 pivots, it's called permutants here, but it's pivots. Basically, the curve here says that we need to process, for example, 10% of the database to get 90% precision. So 90% of what we want to retrieve, we get by only 10% database compare. And this is basically the trade-off. We get, for a huge speed up, 10 times. We do not need to process 100% of the database, but just 10%, and we get 90% precision. It's even better with more permutants, more pivots. With 10% of database process, we get something like 99% precision. So in this case, it's really precise approximate search, almost 100%. But of course, it's 100% never gets 100%. It's always it's approximate technique. Okay, so this was about approximate search, and that's it for today.